6.5 Optimization Problems Part 2, Exploring Solutions. So in the last section in 6.4, we learned how to create a model for an optimization problem. In this section, we are going to explore the patterns in a feasible region to predict where the maximum and the minimum values of an objective function will occur. So how do we know which points are worth picking? How do I know if I want a higher x value, a lower x value, somewhere in the middle for my y? How do I know which one's going to give me that maximized cost or profit, or minimized perhaps, if that's what the question's asking? So let's look at that in this example here. A company does custom paint jobs on cars and trucks. Due to the size of the workshop, the company can paint a maximum of 8 cars and 5 trucks in one day. The total output for the shop cannot exceed 10 vehicles in one day. The company earns $400 for a truck paint job and $250 for a car paint job. How many of each should they book to earn the greatest profit in one day? So you'll see in this example, they didn't actually use the term maximize profit or minimize, but we see greatest, and it's implied that that's what we want to maximize here is our profit. How can we make the most money? So let's identify our variables and state some restrictions. So let's say x will be the number of cars. Let x equal the number of cars. And let y equal the number of trucks. We know here the constraints, x and y need to be elements of our whole numbers because we can't have negative cars come through, and I also can't paint half of a car. So x needs to be element of whole numbers and y needs to be an element of the whole numbers. Our objective function in terms of profit. So I want the greatest profit. So P equals, let's go find our terms of money in this question, $400 for a truck, $250 for a car. We need to write that in terms of a function. So 400 for a truck, and we said y was our trucks plus 250 per car. Now we want to look for some constraints with our inequalities in this question. So I know that I can only have a max of 8 cars and 5 trucks in one day. So my cars, which is x, needs to be less than or equal to 8. Cannot exceed 8. And my trucks, which is y, must be less than or equal to 5. Altogether, I can't exceed 10 vehicles. So x plus y needs to be less than or equal to 10. Those are our 3 constraints. Again, just changing the order here so that we have it in our y equals mx plus b form. My third inequality is y is less than or equal to negative x plus 10. I'll be graphing x is less than or equal to 8, and y is less than or equal to 5. So x is less than or equal to 8. That'll be my blue one. Finding my vertical line at 8, going up by 1s, 1, 2, 3, 4, 5, 6, 7, 8 is here. It's equal to, so I'm going to have a solid line. And it's less than or equal to 8. So I want to remind myself I need to shade to the left of that line so I can cover my x values that are less than 8. My red graph will be y is less than or equal to 5. So going up by 1s as well. Here's my 5 line. It's solid due to my inequality having an equal sign. I want to shade underneath that line as it's less than 5. And then my third inequality, y is less than or equal to a negative x plus 10. So a negative slope and a y-intercept of 10. Here's my intercept. I'm going down 1 over 1. And I want to connect these dots with a solid line as well, as it's less than or equal to. And it's less than, so I want to be shading underneath that function, inequality. So what space satisfies the area for all 3 of those? You want to highlight that. Underneath the green and the red and to the left of our blue graph will be all of this area in here. This is my feasible region. This is just like we did in 6.4, so nothing new yet. That's for the next step. This next question says, find the value of the profit throughout the feasible region and state any patterns that we noticed. So we want to come to the conclusions. We want to try a bunch of points that we see in this feasible region. So I see 0 and 0. Let's just pick, let's say 0 and 5. Zero and 5, say 1 and 4. Just pick any points that you see. 1 and 4 there I circled, 2 and 1. Say 4 and 2. We're just picking a bunch of test points. 5 and 5. Try that one. Maybe 8 and 0. Or 8 and 2. Some corners here. So I've got lots to work with. So let's write those points out and find the value of the profit if those points were put into our optimal or our objective function, sorry. So our first point was 0 and 0. If I put that into P equals 250 times 0 plus 450 times 0, my cost or the amount of profit I'm going to make is 0, which makes sense, right? If I'm going to paint 0 cars and 0 trucks, I'm probably going to make $0 as well if I'm not going to do any work. Trying 0 and 5. So if I don't do any cars and I paint 5 trucks, 250 times 0 plus 450 times 5 gives me a profit of, let's see, $2,000. What other point did we pick? We picked 1 and 4. So 1 car and 4 trucks. Would make me a profit of $1,050. If I do 2 and 1, 2 cars and 1 truck, gives me a profit of $900. So I was doing good. Now I'm going down. I'm lowering my profit. Let's try 4 and 2. Gives me a profit of about, oh, this looks better, $1,800. Try our 5 and 5. 250 times 5 plus 450 times 5. My profit is now $3,250. Got a few more points left just to check. 8 and 0 was another one that we plotted. Oops. P equals $250 times 8 plus 450 times 0. Profit drops a little bit to 2,000. And the last point we had was that other corner, 8 and 2. Will give us a profit of 2,800. So we can see by looking at these compared to where their points are, some of our highest values were closer to the right, like higher up. Max values are up and to the right, and then our lowest values were closer as we went down and to the left. So we want to try to picture that. Up and to the right is where our highest costs have been so far, and our lowest cost, our lowest profit has been down and to the left. A reflection here, so what happens to the value of the profit as we move left to right? So as on our graph, as we were moving left to right in comparison, so say comparing 0 and 0 to 2 and 1. So $0, when we went to 2 and 1, we're at 900. When we got to 4 and 2, we moved right and we got larger yet. When we moved over to 8 and 2, We're even larger, 2,800. So as we're moving left to right, our profit is increasing. The next question, what happens to the value of the profit as we move from the bottom to the top? So let's look that way. Very similar, 0 to 0, we're at 0 still. We're moving higher, we're at a 2 and 1, we're increasing. If we go up to our 1 and 4, we increased to 1,050. We went higher yet, 0 and 5, and we increased again to 2,000. So even still, going down and up, we also see our profit increasing. So think if we increase going right and up, we should see our greatest increase. So profit continued to increase. What points in the feasible region resulted in an optimal solution? So which one do you think we would want? Which one had the highest? Let's reflect back here. Let's look at our chart. So farthest up and farthest to the right. Our farthest up would have been our 5 and 5 point right here. 5 and 5 would be our highest up, and farthest to the right was our 8 and 0. Eight and 0, our profit was 2,000, and our 5 and 5, our profit was 3,250. So always check. Let's leave ourselves a note. Always check furthest up and furthest to the right. So our maximum out of these two so far is 5 and 5, which is $3,250. The minimum possible value of the profit, where did that exist? Well, that was right in the bottom corner where we saw $0. Always check your furthest left and your furthest down. So for the minimum, furthest down and the furthest left. So in summary here, the optimal solutions to objective functions are represented by the vertices. So you could see any of our optimal profits that we found there, our 0 and 0, our 8 and 0, and our 5 and 5 that we checked, all happen to be vertices, which I mean corners on that shape. So this was our 0 and 0. This was our 8 and 0. Our 5 and 5 that we checked. All of those optimal ones are going to be on the corner. So you want to check all of those vertices first, and we don't really have to worry about what's in the middle so much. Only the possible answers will exist in that, but if we're looking for optimization, we want to look for those vertices, the intersection points of those lines, and the corners they make with the axes. If one or more of the intersection boundaries is not part of the solution set, the optimal solution will be nearby it. We can verify each optimal solution to make sure it satisfies each constraint by substituting the values of its coordinate into each linear inequality in the system. So what I mean by that is our constraints over here, x is less than or equal to 8, y is less than or equal to 5, and y is less than or equal to negative x plus 10. If I pick, say, our optimal point that we said was 5 and 5 into those points, let's verify. So x is less than or equal to 8. Well, our x value in that one is 5. So 5 needs to be less than or equal to 8, which it is. Our other one is y is less than or equal to 5. If I plug in 5, 5 is less than or equal to 5, so that still works. And our other one, which was y is less than or equal to negative x plus 10. When I plug in a 5, is less than or equal to negative 5 plus 10. 5 is negative 5 plus 10, which is 5, so that also satisfies. So you also know that each vertice will satisfy your constraints that we stated at the start of this question. Your assignment is on page 334, number 1 to 3. Come see me at the back when you have questions.